Okay, so good afternoon, everyone. So it's my great pleasure to introduce the next keynote speaker of today, Professor Stefanie Gil. She's an assistant professor at Harvard University. Previously, she was at the Arizona State University. She did her PhD and postdoc at MIT. And the fun fact is that we were actually sharing the office for 2 years at the back at MIT. You probably know her already from her great work. She works on trust and coordination in multi-robot systems. And in particular, she is looking at how to use wireless signals to improve that coordination and resiliency in multi-robot systems. For her work, she has received several prestigious awards, such as an NSF Career Award, the ONR Young Investigators Award, and she is also a 2020 Sloan Research Fellow. So without further ado, Stefanie, we look forward to your talk.
Great, thanks so much, Javier. And it's really great to be there with everybody virtually. So I guess I'll just go ahead and get started. So as Javier mentioned, I work on multi-robot systems and in particular the aspects of situational awareness and secure coordination. And that's what I'll talk about today. And to get started, I'll start with a motivating idea. And so I'll go back to the first time that computing systems were able to be connected over large distances and information exchange was enabled remotely. And for example, with the internet. So this really changed the world around us. And the newest phase of that revolution is the one that we're still living in today, which is where information exchange was enabled despite mobility. So this is the mobile network, for example, cell phones, laptops, etc. And that again really changed the world around us and how we operate and how we interact with each other. And so now thinking about the new phase of this evolution, we think about the case where now connectivity is enabled not despite mobility, but actually by mobility. And so this is the multi-robot network, where in particular, controlled mobility is an important characteristic of these systems. So what might this look like? Well, we're already starting to see what the future could look like with multi-robot networks. For example, connected vehicles that can exchange information on the road and use this to arrive at safer, more efficient transportation for everybody. Constellations of delivery drones that can help essentially with services, remote services. During the pandemic, we've seen how important that could actually be. Constellations of CubeSats, for example, or other sensors that can help sense the environment, or search and rescue robots that can work alongside humans, allowing us to essentially reach places that are difficult or dangerous to do on our own. But in order for us to really achieve this future and multi-robot systems to really achieve that potential, there are many challenges that need to be addressed, and that's what we do as researchers, is try to understand what those challenges are and actually address them. So in my lab, we look at two particular challenges in this domain. One is situational awareness for these systems, and the other is trust for these systems. So what I mean by situational awareness is that these robots must know their own state as well as their neighbor's state. They must be able to share information with one another and make decisions based on that shared information. And then along the lines of trust, how can we validate the information that these systems are using to make their decisions? And how can we make sure that their algorithms, their coordination is actually secure? And the research theme that's common in my lab and in my work is the idea of using controlled mobility, which is one of the new aspects of these multi-robot systems when compared to other traditionally connected systems, and communication. So how can these two pieces, the control and the communication, couple in order to enable these multi-robot systems with new capabilities and to make them more resilient? So today I'll talk about three main directions that we've looked at in our work in the lab. One is communication as a sensor, so using the communication itself, the physical channels, as a way to sense the environment or perhaps information about other agents in the network. trust and resilience for these systems, and the role of information exchange in learning for these systems. So I'll talk first about communication as a sensor and what I mean by that. So I'll start with this motivating example here, which is to say that robots oftentimes have to operate in pretty difficult environments, but at the same time, they need to know information about each other in order to be able to perform their tasks. Unfortunately, knowing that information can be made difficult because oftentimes these environments are non-line of sight, they might be operating without a common reference frame, and there's oftentimes no central server to be able to orient them. And so becoming disoriented or losing information with regards to one another is a common occurrence, unfortunately. And so in this example, looking at an example of, say, mapping and pose-graph optimization, you might have agents, say in this case there's two, that are operating in environments where they don't always have line of sight to each other, and they're trying to estimate their pose and perhaps the pose of the other agents in the network as well. And as a result of not always being able to sense the other agent or share a common reference frame or landmarks, the error in the pose estimation can grow over time, which is shown here as a red hashed line. So looking a little bit more deeply at that example, if you have two robots and they have some shared observations to try to reduce trajectory error, and an example of this might look something like the following, where you have the difference between reported relative poses and estimated poses are weighed in a way that's dependent on measurement noise. And the goal is to minimize this over time. And what that might look like is something like this, where at every rendezvous opportunity, they're able to share information and reduce their error. But if there's no way to ensure that rendezvous happens often enough and information exchange happens often enough, you might get a blowing up of the error. And in particular, I wanted to make 2 points. One is that the correct selection of these weights can play a major role in reducing the effective outliers, and lack of data exchange can also result in large trajectory errors. So one idea is that there's information that's already latently existing in the inter-agent communication channels. So if we understood how to exploit that in our coordination algorithms, then this could actually be pretty useful. And so the idea overall is not entirely new. Actually, this idea of sensing over physical channels for cyber-physical systems and sensor fusion is something that's very active, a very active area of research now. For example, using information about localization and using that for validation, watermarking, where you might insert some information inside of signals. Residual analysis using observers can be used to make these systems more resilient, and wireless signal processing. So actually extracting information from the wireless signals that are being communicated amongst the agents. And our work falls mostly into this last bucket of wireless signal processing. And so to give you an idea of what I mean, here's a signal source and say 2 antennas. And this is the bearing direction. And you might want to know that, the relative direction between any 2 agents that are communicating. Now, if you know a lot of other information, such as the frequency of the signal, the distance between the antennas, you can actually back out that bearing angle pretty easily. Now, if you have structure in the environment, which is often the case, actually always the case, then it becomes a little bit more complicated where you might not be able to resolve those angles. However, if you use the mobility of the robot and take several snapshots of this signal channel as the robot moves, then you can actually emulate virtually a multi-antenna array. And so we've looked at this problem and we have some results over a long period of time. The most recent results that we've been able to accomplish, and actually this is something that's on archive now, is that we're able to emulate antenna arrays over free motion in 3-dimensional space. So that means quad rotors and basically different types of robot platforms. So now we can emulate an antenna array along the direction of motion of these agents. And why is that important? Well, it allows us to measure directional signal strength between 2 robots. And this is different from your standard signal strength, because standard signal strength doesn't have directional information. And this is important because it allows us to have generality to different environments. So if there's obstacles in the environment, such as this, you would actually be able to measure that in your signal profile and use that directional information in your controllers. So going back to the PGO problem, imagine that we have the ability to perform active rendezvous, where your agents are exploring the environment. If their error exceeds a particular threshold, they can request an active rendezvous. And then agents that are closer by with regards to their communication strength can actually start to navigate towards the robot. And again, they're using the directional information to know how to navigate. So this is all local sensing and doesn't require a centralized server or even line of sight. So looking back at the example here, the way this might work in practice is that an agent has stopped to request active rendezvous because their error has exceeded a particular threshold. And then another agent that's nearby can start to sense over the wireless signals and navigate towards the other robot in order to initiate an information exchange. And this can be done using pings. It doesn't have to be actually any data that's being transmitted over the signals. And so pings can be transmitted at much longer distances than, say, actual data or maps. And importantly, this can work, or something that we've shown can work, in three-dimensional spaces or even in visually degraded environments, because you're using the wireless signals for sensing. And so the results of what that might look like is, now that you're able to actually have active rendezvous, you can have bounded errors within a particular threshold. And it also can help with outlier rejection. For example, we were able to show that this information can be used to appropriately weigh the shared observations between agents. So now I want to talk a little bit more about trust and resilience in these systems. So feeding off of the idea of sensing over communication channels, can we also use this as a measure of trust and validation of information between agents? So the question that we ask here is, what happens as we take these multi-robot systems into the real world? Now, security is a big issue, as we know, for our traditional network systems. And a lot of really interesting research has been divulging the vulnerability of cyber-physical systems and cyber-physical multi-agent networks as well. And there has been work on exposing the vulnerability of the coordination algorithms for these systems. So for example, take the example of consensus. A classical result here is that agreement can be attained if and only if the number of malicious agents is less than half of the network connectivity. And this result has been originally derived and also re-derived, and there has been many works that have built upon this result. However, unfortunately, being able to ensure these constraints, like less than half of the network connectivity is malicious, this is actually difficult to do oftentimes in real world environments. And so the idea here is that if we could better understand and exploit the inter-agent communication, then we might be able to arrive at more resilient systems. And the goal that we strive for is, can we actually arrive at novel resilience performance guarantees by using this additional information? So to give you an idea of what we're thinking here is that, imagine you have two agents that are communicating and you have the directional signal strength for each of these edges in the graph. Then we can think of these almost as a wireless fingerprint for each set of communicating agents. And the important thing is that if you have a malicious agent that's staging some type of attack, in this case, it's a Sybil attack where an agent might masquerade as several unique identities, but is actually the same physical agent, then the fingerprints for that agent will look largely the same to within noise if you're able to sense over the communication channels. So while your malicious agent can spoof message content, it cannot spoof physics as easily. And so we were able to show a particular result that those wireless fingerprints can be used to derive a value alpha that ranges between 0 and 1 and has a really important property that in expectation, these alpha values are close to 0 for a malicious agent and are close to 1 for a legitimate agent. And intuitively, that alpha captures the uniqueness and other physical properties of the signal. And we were able to show this in actual experiments as well. So it's not just the theoretical results, but we do see from our experiments that the theory aligns pretty well with what we saw in actual experiments in terms of the alpha values are bounded close to 0 for the case of a malicious agent and close to 1 for the case of a legitimate agent in expectation. And this is what the fingerprints look like in reality. So you see for a spoofed agent such as this one, they look largely similar qualitatively. So generalizing this idea, we define a term, the stochastic observation of trust, which we define as an alpha that takes values in an interval between 0 and 1 and represents the probability that an agent J, which is a neighbor of I, is actually trustworthy. And so now every message that's related or that's conveyed by some agent can be tagged by its particular alpha value, where we have the important result holding that in expectation, those alpha values will be close to 0 for a malicious agent and close to 1 for a legitimate agent. And the idea is that given stochastic observations of trust, if you have this additional information, you can use this and you can exploit this to arrive at more resilient coordination. And so looking back at the consensus problem, if each agent has some value X at time T, and you think of each agent updating their own value as a weighted sum of the values of its neighbors, where these weights indicate the influence of some neighbor J on robot I's updated value, then your consensus dynamics looks something like this. So this is just rewriting the consensus dynamics in a matrix form, where you have the malicious node weights and the malicious node dynamics, which we assume are unknown, and the legitimate node weights. And then the legitimate agents, just to be clear, are those that follow the consensus protocol when they update their value X, and the malicious agents are those agents that are not legitimate. And the subset of malicious agents is unknown. So our objective here is to derive consensus weights that are now a function of these stochastic observations of trust alpha ij, and to allow for some observation window T0, where each agent can observe the network and collect alpha ijs, and then start consensus after observing the network for some time. So if we do that, our goal is to solve the following problem. We want to take the difference between the legitimate node value and the true average that it's trying to converge to. And we want to bound that within some error, that's the adversarial influence of the malicious agents, within some given probability. So pictorially, this is what it might look like. If this is consensus and this is the true average that you'd like to converge to, this difference here is what I'm calling delta. It's the adversarial influence. And beyond just achieving convergence, which is important in its own right, we also want to be able to bound the influence by some delta max that we can actually characterize. So that's the goal. And looking again at the consensus protocol and making some assumptions clear. So for example, we require a sufficiently connected graph. And what I mean by that is if you remove the malicious agents from the network, then the network overall is still connected. And we assume independence of our trust observations. And that in expectation, these alpha ijs are distinguishable under the attack, no attack case. And the idea is that if these stochastic values of trust are available, then this allows for stronger performance guarantees than what we could arrive at under classical results. And so how do we actually do this? So I'll pull back the hood a little bit and explain what's going on. So if this is the consensus dynamics of your legitimate nodes, the consensus is going to be influenced by two terms. One is the influence of other legitimate nodes on its value, and the other is the influence of malicious nodes on its value. And our approach is to show that if we take a running sum of these alphas, which I'm going to call beta here, the probability that beta is greater than 0, and I'm going to actually shift these by 1/2, so that now alpha is in the range of -1/2 to +1/2. So that if that beta is positive for a malicious edge or negative for a legitimate edge, then this constitutes a classification error. And I want to show that this decreases exponentially in time. So the possibility of misclassification decreases exponentially in time. And I want to be able to show that both of these terms converge to a finite limit almost surely, which implies convergence, and that the bound on the influence of the malicious nodes can be characterized. And lastly, that we want to also understand the characterization of this error as a function of T0, which is the amount of time that I'm allowed to observe the network. So I'll go to the first result, which I'll just explain here without going through the proof, but I can, the paper reference is on the next page. But the idea is that if we have these random variables beta that are a running sum of the alphas, the probability of misclassification, which means I misclassify J as malicious when it's legitimate, or vice versa, is actually bounded exponentially in the amount of time that I observe the network. And so an important corollary of this is that the failures or misclassifications occur only finitely often in the limit. And this implies that the influence of the malicious agents can indeed be bounded. And so that's one of the important results that we were able to show here. And this leads to the first result, which is that we are able to achieve convergence even in the presence of malicious agents and independently of the number of malicious agents in the network, which is different than the classical result, where the number of the malicious agents had to be bounded. And then secondly, beyond convergence, we're able to show that this bound here, this delta max, can actually be characterized, and can be characterized in the following way, which I will just refer to the paper for more details on what exactly these terms are and how to compute them. But one thing I do want to point out is that they are a function of the time that you are allowed to observe the network. So a direct function of how many stochastic observations of trust you're allowed to accrue before actually performing consensus. And one nice thing that I should mention is that you can drive this error term arbitrarily lower by allowing a larger observation time of the network. So what this looks like in an actual experiment. So this is an experiment for coverage. In the case where you have a spoofed cluster of nodes and you have no observations of trust, stochastic observations of trust, then your control is going to drive the robot into an arbitrary area of the environment. However, if now your robot is actually allowed to sense over the wireless channels, and you were to integrate that into your coverage control laws, then we show that your control will now converge to within an epsilon vol of the nominal result, which is the case where you don't have malicious agents. And I'll mention that because the number of observations here is very important, it's important to be able to accrue as many observations as possible. And so another part of the work that we look at here is the role of neighborhoods and how neighbors and exchanging observations with neighbors can actually improve your ability to converge faster. So I've talked about using sensing over communication signals to help with situational awareness and perception of other agents' states, and how that information can be used to actually achieve stronger performance guarantees for some multi-agent coordination algorithms. And now I want to talk briefly about the role of information exchange in learning for these multi-robot networks. And the question here that we focus on is, how do we know what to communicate and when to communicate? And knowing that is imperative for the performance of these systems. So here's a particular problem that we look at. This is a pipeline repair problem where you have a network of locations that have possible damage. And the agents are deployed or tasked with deploying over this pipeline to actually repair these sites. And there's partial observability, meaning that there's a fixed number of repair sites with different damage levels. And the agent only knows for sure what the damage level is when it's actually able to visit. And these damage sites evolve in time according to known Markov chain dynamics. And then once a site is fixed, it's fixed and it can no longer fall into disrepair. And we want to find a particular deployment strategy for how these agents should deploy in order to fix the pipeline in the minimal amount of time. And one thing that I should point out is that this problem is analogous to many different problems, including, for example, drone deliveries, any problems where agents must physically move to a site in order to service it. So drone deliveries or other services of this kind can also be modeled within this framework. So one way to solve this problem is to employ a greedy-based policy. So it's to say any agent, as it's moving through the pipeline, if it finds a location that needs to be repaired, then repair it. Now, this is very simple to implement. The downside of this is that oftentimes, because the agents here are not coordinating with each other, and they're just using a greedy strategy, essentially, they might end up repeating work, as you see here. And so that's something that we would want to avoid for sure. So how can we do this while essentially not having to complicate the control too much? So this is easy to implement, but it results in no coordination. So what's actually going on here? One way to solve this problem optimally is, of course, a dynamic programming approach. But as we know, a dynamic programming approach will become very quickly intractable, especially for partially observable states, for example, the pipeline repair problem. So that's not really an option. Another option that we investigate is the use of rollout policies. And so the idea here is that we use rollout to approximate the future costs of a particular action. And the important observation about using rollout in this context is that it was shown to have a cost improvement property, where by using this approach, you will actually improve on the cost over your base policy. And so what does that allow us to do? If we now use one agent at a time rollout, where each agent will essentially optimize and decide its decision based on this rollout framework, as I showed in the previous slide, you actually arrive at a much better policy, where importantly, and this is the observation that I'd like to make, that even using a very simple greedy strategy as your base policy, coordination arises naturally. And so that's a really important observation that we want to be able to exploit. However, one thing that I did not mention was the role of communication. So here in this framework, communication requires, there's a lot of communication requirements. The agents have to coordinate, so they have to be able to communicate their actions, their beliefs, etc., which might not be realistic in real scenarios for robots. So one question that I pose and that we pose in our research is the question of, well, what could be the role of cloud connectivity for our systems? So we've gotten to a place where we're very comfortable with the notion of being connected all the time. Well, what does this mean for our multi-robot systems? And can we exploit this in some way? So we consider the following framework, where we assume that there exists a cloud server, and while we're not always connected, we can be connected within some probability rho. So we allow for intermittent connectivity to this cloud server. And when it's connected, we continue doing one at a time agent rollout. And when we're not connected, we use some prediction or some model of the future the future actions of our neighbors. And so what happens in the case where we do not allow communication is that you might end up with very silly behaviors where your agents actually get trapped in a cycle such as this one, and they're not able to progress in actually repairing the pipeline. But the interesting observation is that with just a small probability of intermittent communication, in this case 10%, what we observe is that that might be enough to actually get these agents out of such cycles where they can start to progress on repairing the pipeline. So they're very interesting questions of communication to be addressed in learning as well. And one point that I'd like to actually make here is that we've also looked at completely different classes of problems. So in this case, we're looking at cloud cluster networks where you have a cloud and small local clusters of agents. And the objective here is to detect an event. And so actually have distributed detection of an event of interest in the environment, where the objective of the cloud is to determine whether the event is occurring, so a value of 1, based on the inputs of the observations of these local clusters. So this is a completely different problem. However, what we find here, and in the paper here that was published in GlobeCom, we were able to show, using a principled approach, that the communication, that even with a very small probability of communication, again, here about 15%, we're able to reduce the expected loss in detection, and that even with higher probability of communication, you don't actually get much better performance. So it seems that even a small amount of intermittent communication can make all the difference for these systems. So I think that's a very interesting avenue to continue exploring, and I see that as being a potential model for communication of our multi-robot systems in the very near future. So I'll summarize with a few observations here. So today I've talked about the concept of using communication as a sensor in multi-robot systems, and I've shown how that can be used to enhance situational awareness and also to change the way that we think about trust and resilience in multi-robot systems. And an observation that I'd like to make here is that as multi-robot systems become more prevalent, these systems are physical and they have many physical channels of information, such as visual channels, wireless channels, many different that we can actually start to exploit to validate information. I think that's going to be really important for their security. And then lastly, we talked about the role that communication and information exchange can play in making these systems more capable in terms of their sequential decision-making abilities. And in all of the work that I've talked about today and that we focus on in our research, mobility and communication and the coupling between these two play a very important role. And so a few concluding remarks that I'd like to make. This is a really exciting time for multi-robot networks. I really do see this as a cusp of these systems becoming a lot more available in the world around us and really changing the way that we operate as a society. And then understanding the connections between communication and control is very powerful for these systems and can lead to a paradigm shift in their capabilities and their resilience. Cyber-physical systems bring novel opportunities for data validation and also establishing this notion of trust, inter-agent trust and data validation. And formalizing this notion of trust allows for new mathematical models and novel resilient frameworks for multi-agent coordination that allows us to arrive at stronger performance guarantees than under a classical view of these systems. So I'd like to acknowledge, make a few important acknowledgements. So my students who work very hard and have done a lot of the work that I've presented today, as well as my collaborators who were also featured very prominently in some of the works that I've talked about today. and also the sponsors, of course, that without their support, the work would not be possible. And so with that, I will leave you all with a few concluding remarks, and I'm happy to take any questions.
Yeah, thank you very much, Stefanie, for the great talk. So for those of you joining virtually, you can ask your questions in the Ask Q&A function, or also raise your hand. For those there in place, you can raise your hand and someone will bring you a microphone. Let me kick off with one question. So I was wondering, you talk about the spoofing of a real system that spoofs virtual agents. What will happen if someone controls a physical system and then can in that manner influence the multi-robot system? And how will you deal with that situation?
Yeah, that's a great question. So one of the ideas there for the spoofing is that one agent can spoof many different entities. And in fact, by doing that, that's how they can have the most detrimental effect on your coordination. So it is definitely possible that the agent can physically move and then spoof a new entity. But by requiring that it physically moves every time it needs to spoof a new entity, you do limit its ability to be able to detrimentally affect your algorithm. It's definitely lower cost to not have to do that. But even in that case, I think there could be some interesting questions about correlation. So perhaps there's enough correlation between their signals as they move to be able to say something. We haven't done that research. I think that's still an open question, but it's an interesting one nonetheless.
Thanks. Do we have any questions in the room?
Questions in the audience? Yep, we have one up here.
Thank you. So, well, very nice talk. Thanks a lot. And I was wondering, when you mentioned about the resilience part, you mentioned that you need to have a sufficiently connected graph. I was wondering whether you have a reactive component in that. I mean, are the robots able to understand if they are meeting the requirements, or are you envisioning any way of actively enforcing these requirements on connectivity?
Yeah, that's an excellent question. Thanks for that question. Yeah, so that's an important area of research, I would say. So in the work that I presented today, we're mostly dealing with static networks where the networks aren't changing over time. So agents don't necessarily have the ability to move and make new connections. So the sufficiently connected requirement is similar to, say, your typical connectivity requirement that you assume that at time 0, the graph is connected. So it's not too dissimilar to that. But the question of, can I use these observations as part of my control, my positional control, in order to be able to create a sufficiently connected network over time? So as I start gaining observations and I start understanding which agents I can trust and which I cannot, then perhaps every agent can also be enabled to move and change their neighborhoods. That's a really interesting question, which we haven't done yet. So as of now, we just have to make this assumption. But I see a path forward where you could use this information dynamically in a positional controller, or where agents can have some ability to change their neighborhoods.
Thank you.
So I think we have a related question in the chat. So it also refers to not the static case, but when the malicious agent moves around and makes the network dynamic. Specifically, what if the dynamic of such motions, so of the malicious agents, is faster than the detection dynamic of normal nodes agents? What will happen then?
Yeah, that's also a really great question. So there are a lot of very interesting questions when you start thinking about the dynamics, and that goes back to the goal of making the observation window as small as possible. So you want to be able to make these determinations of trust as quickly as possible, and there are two ways that we've started to address that. One is by showing that the rate at which you can accurately determine trust actually decay, or it grows exponentially. So the more observations you have, you get much more quickly to the point where you can very accurately make an assessment of whether you can trust an agent or not. So making that observation window as small as possible. That's part of what we mentioned. And maybe I can actually show for those who are interested in seeing more about that result, I can just point out the particular paper reference. So this paper right here talks a little bit about that, in particular, the rate of convergence. And then the second place where we actually start to address this is by using the neighborhood. So this is the other. Can you still see my screen, by the way?
We cannot see it now.
Oh, okay. All right. So let me, it sounds like I lost. Okay. So
now, yes.
Okay, perfect. So this is the other idea here. So using or leveraging as many observations as you possibly can to arrive at those, to arrive at accurate assumptions or accurate determinations of trust. So those are the two places where we look at that. And these two results are actually in twin papers that were published in TRO this year.
Questions from the audience?
Can I ask one more question? Sorry about that.
Yeah, this is the other paper, by the way, for the convergence rate.
No, my second question was about the last part of your talk when you mentioned about the fact that you can consider intermittent connectivity. And actually you model, if I'm not wrong, you modeled it as having a probability row of having perfect connectivity and 1 minus row of not having connectivity at all. Mm-hmm. How about having like poor bandwidth? So, I mean, very often it happens that you are somewhere and you don't have 4G, you have only poor, crappy connection.
Yes. So in other words, having some compressed data ability.
Yeah.
So not 0 or 1. Yeah, that's actually a really interesting question. I haven't looked at those questions yet, but definitely a worthwhile direction to start thinking.
Thank you.
Thank you.
Do you have any more questions in the chat?
Doesn't look like someone raised the hand, but then lowered it. So I guess that question is not there anymore. I do have another quick question in the meantime, Stefanie. To which extent, to which precision can you detect other agents from the Wi-Fi signals? So this relates mostly to the first part of your talk.
Oh, I see. Okay, so yeah, that's actually a really great question as well. So in that paper that I referenced, that was from the International Symposium on Robotics Research Conference, what we show is experimentally what the error profile looks like. So how well you can determine the direction or the direction between or the relative direction between any two agents. And we found empirically that it looks very Gaussian in form. And so we believe that this can actually be approximated at least as a Gaussian. And some of the experimental results are in that paper.
Thanks. Amanda, do we have more questions in the audience?
Maybe
in person?
One last question.
Yeah.
I'm scanning the room.
So I guess it will be the last question.
I think we're done on this side.
Okay, so then we are perfectly on time. So thank you very much, Stefanie. Thank you everyone for attending.
Thank you so much. It was really wonderful to be able to speak with you guys today.